Hello and welcome to my presentation at the Strasbourg Symposium on Usability and Design. The work presented here is about methods to assess usability. I will present some ideas on how eye tracking can be used to examine how users work through instructions for use. Moreover, I will present preliminary results of an eye tracking study that can illustrate the potential of the specific setup we developed, both to address questions from prior research in new ways and to address new questions. Procedures that guide users step by step in performing a task play an important role in many instructional materials, such as user guides, tutorials, or online help systems. However, designing effective procedures remains a challenge, in particular regarding which information to include in a procedure to effectively support users and how to present that information. Since the early 80s, a lot of research has been conducted on the components of a procedure and on how users actually deal with procedures. As a starting point, I would like to emphasize two findings. First, users process procedures very selectively and often partially. They attend to certain parts of a procedure but skip others, with what they attend to and what they skip varying depending on factors such as goals they pursue and context of use. And perhaps related to that, users sometimes have problems following directions given in a procedure. All this was already observed in the by now classical studies by John Carroll and colleagues and confirmed and extended by many studies later on. Findings like this strongly suggest that to support practitioners in designing effective procedures, we need to understand how users actually deal with procedures. In particular, we need to understand which information users select from a procedure, how they process that information, and how they finally put it to use. Understanding how users select and apply information is also important from a research perspective. To understand the effect of a design variable, such as adding screenshots to a procedure, we not only want to know which overall effects that variable has, such as more efficient and effective task execution, we also need to understand how such effects arise, hence in the example here, whether and when users select and process screenshot information and how they use it during task execution. Knowing about the why of an effect will help researchers to better understand boundary conditions of design principles. Many different methods have been developed to study how users select and apply information. However, all these methods have limitations that severely constrain the range of questions we can address. Many studies relied on concurrent think aloud and asked subjects to read out sections they are attending to in a procedure. However, concerns have been raised that the task to think aloud might interfere with what people would normally do. Moreover, some information contained in a procedure is very difficult to verbalize anyway, such as information you attend to in a picture. Hans van der Meij and colleagues combined think aloud with user observation and event logging. In addition to recording what users read when working through a procedure, they also recorded systematically at which points users would switch attention between the manual and the software or device they were working with. So they examined very systematically what users actually do in response to information they receive. However, detecting and classifying user activities required manual scoring, which raises concerns with respect to the reliability of observations. The click and read method is an interesting alternative. With click and read, instructional material is presented with all text blurred except the headings, like shown here. Users have to click on a segment they want to read, and then the text becomes legible, and it is blurred again when users proceed to the next segment. Click and read allows to monitor very accurately what information users attend to, but it can be argued that click and read slightly obstructs the natural reading process. You have to click on information you want to read. You're missing preview information, and information selection is restricted to predefined segments. Eye tracking can overcome many of these limitations. It does not require a secondary task like thinking aloud. It does not require manual scoring for event classification. It does not obstruct the normal reading process, and information selection is not confined to predefined segments. However, eye tracking provides its own challenges, and perhaps the biggest challenge relates to the fact that procedures are typically read to do something. The main user goal is not to read, but to act. Therefore, an eye tracking setup to study procedures will need to enable users to freely decide when to read, what to read, and how to interleave reading and acting. Many setups used, for example, in psycholinguistics do not meet these requirements easily. So, in a typical setup for reading research, head position is fixed and subjects are very restricted in what they can do in response to what they read. Mobile eye trackers, such as eye tracking glasses, could be an alternative. Subjects can then move their head freely and they can act very much like they would normally do. However, tracking accuracy is rather limited. Moreover, mobile trackers produce a video with eye tracking data overlaid. There's no reference image. Extracting data for quantitative analyses from such a video requires a lot of manual post-processing, which can be very time-consuming. To overcome these limitations, we developed our own setup. To obtain data that are sufficiently accurate, we wanted to use a remote eye tracking device attached to a monitor, and we decided to present the instructional material and the software it refers to on the same screen. So, in a typical setup for studying procedures, the instructional material would cover about 1/3 of the screen and be placed to the right of the software it refers to, as shown here. And this is how it looks like in our lab. So we are using for presentation a 24-inch monitor to which an SMI RED eye tracker is attached. With this setup, subjects can move their head freely within the range supported by the eye tracker, and they can interact with the documentation and with the software in a fairly natural way. What we initially get with this setup is a screen video. However, the documentation remains static and does not change until subjects move on to the next procedure on the next page. Therefore, we can create a single reference image for each procedure, which includes the respective page of the documentation, here on the right-hand side, as well as a snapshot of the software while subjects work through the procedure, shown here on the left. This greatly facilitates data aggregation, visualization, and analysis based on specific areas of interest, since now data from multiple subjects can be mapped onto a single reference image. The result can then look like the example shown here. This is one static reference image for one procedure of a tutorial. You see several areas of interest, and you see mapped onto the static reference image the scan path representation of two subjects that work through the procedure and carry out the respective tasks. To explore possibilities of this setup, we ran a simple study that dealt with effects of screenshots on how users work with procedures. We created a simple tutorial containing 8 procedures for 8 consecutive tasks, which subjects had to perform with the GIMP image manipulation program. There were 2 versions of the tutorial, differing only with respect to whether they included screenshots or not. The objectives of our study can be divided in 2 parts. One part was more confirmatory and hypothesis-driven, the other part more exploratory. The hypothesis-driven part checked whether we can confirm findings from prior research that screenshots improve accuracy on tasks and efficiency of task completion. To better understand why such effects would occur, we also wanted to test the hypothesis by Galevy and van der Meij that screenshots improve performance because they help users switch attention between a procedure and the software or device users work with. The more exploratory part asked whether our subjects would select and process screenshots before task execution is attempted, so for planning and preparing task execution, or whether screenshots are processed after the task is executed to verify the result. A second question was whether subjects would adopt an atomized strategy of task execution and process and execute tasks step by step, or whether they would delay task execution and only start until they have processed 2 or more steps. The test session comprised several parts, including the main test, where subjects had to work through the tutorial, and pre- and post-test questionnaires collecting demographic data and data on experience with image manipulation software in general and GIMP in particular. We recruited 42 subjects and assigned them randomly to one of the 2 conditions. We used an SMI RED 250 mobile tracker with tracking rate set to 120 Hz. Experiment Suite Scientific and R were used for running the experiment and analyzing the data. Let's now look at some results. First, we assessed accuracy on tasks. In line with prior research, we found that fewer errors were made if subjects worked with a tutorial containing screenshots. The difference was about 13% and very robust statistically. Regarding time on tasks, we observed that subjects in the screenshot condition tended to be slightly faster. However, the difference was only marginally significant. We also observed a robust negative correlation between time on tasks and accuracy. The more time subjects need, the less successful they are. For the analysis of eye tracking measures, we created a reference image for each task in each condition. 2 areas of interest were defined to analyze the time subjects spent reading the tutorial and the time they spent working with the software. The 2 AOIs were also used to analyze how often subjects switched attention between tutorial and software. In the scan path representation shown here, attention switches are indicated by the saccades, visualized as straight lines crossing AOI boundaries. Looking at the fixation times, we find that adding screenshots significantly reduced the time subjects spent working with the software. On the other hand, screenshots did not significantly reduce the time subjects take to process the procedures. We interpret this pattern to mean that adding screenshots facilitates planning and actually executing the tasks, but not reading and processing the procedures guiding users through these tasks. Let's now look at how often subjects switched attention between tutorial and software. Numerically, there is a small effect, but in the opposite direction compared to the Galloway and Van der May findings. There are slightly fewer attention switches if screenshots are available. However, this effect should be treated with caution. Whether it reaches significance or not depends on the specific statistical test that you apply and whether or not the analysis is run on raw data or log transformed data. For the exploratory part, we zoomed into the procedures and inspected more carefully how action steps and screenshots were processed. What you can see very clearly by looking at a scan path like shown here, working through a procedure is a highly fragmented process. Reading and acting are tightly integrated. This is not an entirely new insight, but there seems to be more switches than previously reported based on, for example, studies using the ISTE method. A first question we asked was, are screenshots processed at all, and at which point are they processed? What you see here is 5 seconds of the scan path immediately before the action described in step 1 of this procedure is executed. That is, before the required click is made in the GIMP software. At this point, several fixations were already made on the respective screenshot. So the screenshot was selected and processed to plan and prepare the action. This pattern was found in the majority of cases, but Other screenshots tended to be processed after the action was completed, that is, to verify the results. We noticed there was large variability regarding the screenshot usage pattern across subjects. There was also large variability across screenshots, with some screenshots processed always to plan and prepare action execution, and others most often to verify the result. It seems that design factors such as screenshot size and in particular the signaling technique do have an impact here. To explore whether subjects adopted an atomized or a delayed execution strategy, we analyzed how many steps subjects processed with each task before the first action was actually executed. We found that subjects predominantly adopted an atomized strategy. They processed and executed procedures in a step-by-step manner like seen here. The subject processes step 1, including the screenshot, then executes the action, and then moves on to step 2. This tendency is even stronger if the first step includes a screenshot, and it is stronger for longer compared to shorter procedures. Okay, let's summarize the preliminary results of our example study. We found higher accuracy on tasks and faster time on task if procedures contain screenshots. Eye tracking measures suggest that adding screenshots to procedures reduces the time spent working with the software, slightly reduces attention switches between tutorial and software, and encourages atomized step-by-step task execution. The preliminary conclusion we derive is that screenshots support more efficient and more effective completion of tasks. In this respect, our study confirms findings from prior research. Regarding how these effects arise, we hypothesize that screenshots enable users to carry out individual tasks more efficiently and encourage users to adopt a more efficient step-by-step approach to working through procedures. Regarding the potential of eye tracking for analyzing procedures, I hope my presentation has demonstrated that eye tracking provides interesting new opportunities for researchers to catch the user in the act and makes it easier to study how users can select information and act in response to that information. So let's explore new ways of applying eye tracking to technical communication and usability research and advance the method further. Finally, here the list of references I used in my presentation. Okay, I think that's it. Thank you very much for your attention. I'm now happy to take your questions.